So in the last video, we worked out kind of an epic example. We worked it out both ways, and certainly it was really helpful for us to switch the line integral to a double integral. The line integral took a lot of work, 3 different pieces. The double integral was very straightforward. So we, so far, have gone exclusively this direction. We've gone from line integrals to double integrals. And yet, please realize that Green's theorem says these are equal. And so you're certainly allowed to go backwards as long as you set everything up correctly. So I wanted to copy this formula because we're going to want to make sure we know Green's theorem. And then I wanted to ask another question for you that's going to bring us to this question of how can we go backwards. So the question is, can we use Green's theorem to help us solve area problems? Let's recall that the area of a region D, now I'm going to assume that this region D is relatively nice, and I won't get into details of what that means in this video, but nice regions D have area given by the double integral over D of 1 dA. Right? When you integrate 1, you're getting volume, which equals area in this particular case. And so let's think about it, though. Okay, so if I'm going to use Green's theorem, then I want to think about this 1 right here as actually this q partial x minus p partial y. And if I do that, then I can go backwards and switch to a line integral. So to switch to a line integral via Green's theorem, we need to find a vector field such that q partial x minus p partial y is in fact 1. I want this to be that, right? So I'm going to give you a couple of them, and then you can actually check these on your own. But here's 3 of them that work. So here's f of xy equals 0x. Here's another one. F of xy is the vector field negative y 0. And here's a crazy one. F xy is negative y over 2 comma positive x over 2. And you can check in each one of these cases, partial q partial x minus partial p partial y is in fact 1. Let's just see it real quick right here. I'm thinking about this as p comma q, and you can see very clearly q partial x is 1 minus 0 is 1. So this one works out. Here, what are you going to do? You're going to do q partial x is 0 minus negative 1 for p partial y, and you get out 1 again, and so on and so forth. So these are going to be some little tools in our toolbox that we can pull out and potentially work out some area problems. All right, so let's go ahead and see an example of this. And I think in this video, let me just first show you the picture, then I'll break the video and work out the computation. So I wanted to show you the graph of the this region bounded by this particular curve. So this is kind of a clue that you might be thinking about Green's theorem for this problem, because it's the area of a region enclosed by a space curve. Actually, not a space curve, but a curve. So let's go over to Mathematica. Let me pull up my Mathematica app. I've gone ahead and typed it in. Oops, yeah, typed it in, and that's the graph. I lost my pointer. As far as I can tell, I can't point on this screen. I don't think I can. That's okay. But that's what it looks like. And so we actually want to find that area. Let's take a screenshot. We got it. And then we can actually import that into this file. Let's see, photo library, recently added. There it is. Let's insert it, and then we'll crop it, and then we'll break the video. So I think we can click on crop. And then, yeah, let's just do that right there. Okay, so we've got a nice picture now that we can see. And maybe we can crop it some more. Let's bring it down. We don't want to see all that stuff up there. Okay, there we go. So let's break the video here, and in the next video we will come back and figure out how we can find the area of this region that's enclosed by this interesting